You have learnt about probability, current density and conservation of probability in the previous lecture. Today we are going to explain the idea of probability current density by taking some illustrative examples. In first example, I have taken here a beam of identical particles going in x direction is represented by the wave function psi of xt equal to a e to the power I over h cross times px minus et. Here a is actually a constant. And now we have to calculate the probability current density, and comparing with the classical expression, the problem says that we have to check that this probability current density is proportional to flux of the particles in the beam. So let us first of all find the probability current density when this wave function is given. You can see that the wave function is given in one dimension, so we will actually use the result for the probability current density in one dimension. We have seen that the probability current density in one dimension. We have seen the expression for it in the previous lecture, and this is J equal to H cross over 2im times psi star del psi by del x minus psi times del psi star by del x. This expression you have already studied in previous lecture. Now here we are given the wave function psi, so we will substitute the value of psi and psi star here. Psi star, you know, it is the complex conjugate of the given wave function psi, and so substituting the value of psi and psi star, our result will be H cross over 2im into, you can see psi is a into e to the power I over h cross px minus et. So the complex conjugate of this function will be a star e to the power minus I over h cross times px minus et. And then we will have to differentiate psi, and after differentiating psi partially with respect to x, when we will differentiate psi partially with respect to x, we will have to keep t constant. So this will be, in fact, a is constant factor, so it is outside of the differential operator, and this will be a ip over h cross e to the power I over h cross times px minus et, and minus psi. You know psi is a e to the power I over h cross px minus et. And then we will differentiate the complex conjugate of psi star partially with respect to x, and this will be a star minus IP over H cross times e to the power minus I over H cross Px minus Et. This is just a simple differentiation. You can easily see it. And so from here we can see that what will be our result. In fact, you can see that this exponential terms e to the power minus I over H cross times Px minus At into e to the power plus I over H cross Px minus At, this will cancel out and that will be simply 1. And so only the term remain will be A star times A. And similarly in the next term, this exponential factor will cancel out, and so the result will be simply A star times A. And here this minus and minus will be plus. And so our result will be what? This will be H cross over 2im A star times A plus A star times A. And so we can write this expression as H cross over 2im times 2 into mod of A square, mod of A square. And so you can see this will be equal to times also there will be in fact IP over H cross, and here is also IP over H cross. So this will be in fact 2, this will be in fact also IP here, IP, I into P. So you can see from here that this result is equal to mod of A square times P over M. So this is the probability current density, and you can see from this result that the probability current density is just proportional to modulus of A square. And you know that modulus of A square is proportional to the number of particles per unit length, and you know that P by M, momentum divided by mass, is simply velocity. So you can see that J is proportional to mod of A square, and this is proportional to the number of the particles per unit length. Here space is one dimensional, so we say that the number per unit length, and we know that this P by M is equal to V, and this is velocity of the particle, velocity of the particle. And we know the flux of the particle in the beam, which is in fact defined in this problem, will be actually equal to NV, where N will be the number of particles per unit length. So if N equal to number of particles per unit length, per unit length, then n into v. Actually, v is the length covered by the particle beam in 1 second and through a unit cross-sectional area. And so this will be just, or you can say this is one-dimensional case, so this will be the length covered in 1 second, and n is your number of particles per unit length. So this product nv will be actually equal to the flux of the particle. This is flux of the particle in the beam. And so we can say that the probability current density J is proportional to the flux of the particles in the beam. So you can say the probability current density J is proportional to the flux of the particle in the beam. So you have seen that how easily we can actually solve the problem based on this concept. You have only to remember the expression for the probability current density both in 1 dimension and 3 dimension, and you can easily solve such problems. Now let us take another example to illustrate the idea of this probability current density. In fact, in this second example, our problem is we have to calculate the probability current density. J for a 3-dimensional wave function, 3D wave function psi of r equal to a over r e to the power ikr. So there is no difference between these two problems, only the function is different, but we will apply the same technique. So here you can see that the wave function has been given, in fact, in spherical polar coordinate. So we will use the expression for the gradient of psi and psi star in a spherical polar coordinate. In fact, we know that in a spherical polar coordinate, first of all, write the expression for the probability current density, and then we will see what we have to evaluate so that the probability current density can be calculated. We know that probability current density I am writing it here actually in 3 dimension. So we will write vector J, and we know I am just now writing the another alternative expression which we have already studied in previous lecture to clarify that that expression is also equivalent to the original expression. And so I am writing here J is equal to H cross over M times imaginary part of psi star times del psi. Here del psi means gradient of psi. I have used this expression, and you will see this expression is also same useful in calculating the probability current density. Now, as I have told you, this problem, the wave function is given actually in spherical polar coordinate. So we will use the expression for this gradient of psi in spherical polar coordinate. So you know, in spherical polar coordinates, spherical polar coordinates, you know this gradient of psi will be what? We know it is del psi by del r hat plus 1 over r del psi by del theta hat and plus 1 over r sin theta del psi by del phi hat. Here actually r hat, theta hat and phi hat are unit vectors in the increasing direction of r, theta and phi. But as we are given in this problem, this psi of r is equal to a e to the power a over r e to the power I k r. So this is just only a function of r, and if it is only a function of r, you can see its partial derivative with respect to theta and with respect to phi will be 0. So you can see that this del psi by del theta and del psi by del phi, both of these will be 0. And so our expression for this gradient of psi will be what? This del psi is simply del psi by del r hat. And so you can see this will be actually equal to del r, and now let us substitute the value of psi. This is a e to the power I k r over r. Now you can differentiate it, and we will find that this del psi is equal to what? This will be in fact a into I k over r into e to the power I k r, and minus a into e to the power I k r over r square. This is the differential coefficient of psi with respect to r. And again we know that this psi star will be what? This is simply the complex conjugate of psi, and so this will be a star e to the power minus I k r over r. So now let us substitute all these values in the above equation where we have defined the probability current density, that is in this equation 1. So substituting these in equation 1, so using these in one, we obtain what result we will get. You can see that this J actually here there will be also R hat. This is R hat. And so now you can see what will be this J. This J will be equal to, as I have written it in equation 1, this will be H cross over M times imaginary part of, you can see, psi star. Psi star, this is in fact A star e to the power minus IKR over R times del psi. And you can see from here that this del psi is equal to what? This is A IK over R, IK over R, IK over R into e to the power IKR by R, IKR by R, and minus this is A e to the power IKR over R square. And so you can see from here that this A star and A, the product of A star and A will be mod of in fact A. So A will be common here, and the product of A star with A will be, can be written as mod of A star, mod of A square. So this will be mod of A square times H cross over M into imaginary part of, you can see from here, when actually we will multiply this exponential factor by this and this, the result will be simply 1. And so our result is IK over R minus 1 over R cube. 1 over R cube. So minus 1 over R cube. And you can see from here that this is, here actually there is this much over R. So the product of this R with this R will be actually equal to R square, and product of this R with R square will be R cube. And so you can see from here that when we will take only the imaginary part, what is the imaginary part of the term inside the bracket, this square bracket? This is simply K over R square. So this is K over R square. And so you can write this expression as H cross, and in fact here there will be also R hat, and this is R hat. So this is H cross over M times mod of A square, and mod of A square into k over r square. And so you can see that this h cross k, you know h cross k is simply momentum, and so we can write this expression as this is p over m mod of a square over r square. And again, you know this p is mv, and so m will cancel out, and this will be simply v, here will be r hat 2 r hat, so this will be actually v over r square, v over r square times mod of a square times r hat. So this is the probability current density in this case. Now you can see that v is the velocity of the particle, and so physically this result represents a radial stream of particles whose intensity falls inversely with the square of the distance. So this is the remarkable fact which we can see from this result. So you can write physically this represents a radial stream of particles, a stream of particles whose intensity falls off inversely with a square of the distance r. So you have seen that using the alternative expression for the current density, or you can say probability current density, we have solved this problem. So now I hope you are acquainted of both of the expression for the probability current density. Now let us take a third example to clarify your concept, and in this third example we have to show that for any normalized wave packet in one dimension, we have to prove this result. Integral minus infinity to plus infinity j of x dx is equal to expectation value of px over m. Actually here px is the x component of momentum. So now we have to show this result. Actually we can solve this problem simply using the expression for the probability current density in one dimension. And so let us start by that expression for the evaluation of this integral. You can see integral minus infinity to plus infinity j of x dx. what will be this? We know this Jx is equal to what? This is h cross over 2im, and it is a constant factor, so I am taking it outside of the integral. And now there will be integral from minus infinity to plus infinity, and the expression for Jx you can write here. This will be in fact psi star del psi by del x, del psi by del x dx, and minus integral from minus infinity to plus infinity psi del psi star by del x dx. We have used the expression for probability current density in one dimension. Now we will evaluate these two integrals. You can see this integral from minus infinity to plus infinity of j of x dx. This can be written as h cross over 2im. Now write the expression for psi star, and writing its expression for psi star, and you can write this will be 1 over minus I h cross integral from minus infinity to plus infinity psi star of x and minus I h cross d dx psi of x minus cc. What is this cc? I am just telling you. And here actually we have followed an important technique. Actually this factor minus I h cross is not present here, but I have just divided this expression by minus I h cross, and also I have multiplied by it, so result remains same. And here you can see in this second term, at the place of second term I have written cc. What is this cc? You can see this cc is actually the complex conjugate of the first term in a square bracket, because you can see if we will write the full expression, this will be simply the complex conjugate of this first term. So I have written here cc. But remember, all operations are at a particular time t, and so I have used d dx in place of del x. And you can see what is this integral. When you say this is minus infinity to plus infinity psi star of x times minus I h cross d dx psi x. Actually you know this is simply the scalar, this is simply the momentum operator in one dimension, and so from the definition of expectation value you can say that this integral is nothing, this is simply the expectation value of the momentum operator, or you can say simply the momentum px. And so now you can write that this integral minus infinity to plus infinity psi star of x minus I h cross d psi of x by dx dx minus psi of x dx, and actually here there will be also dx, this dx. This is actually the expectation value of px. This is expectation value of px, and so you can see the second term will be simply the complex conjugate of the first term, and you know what will be actually the first term. So you can see, so the first term is 1 over minus I h cross expectation value of px, and since this cc is the complex conjugate of the first term, so what will be this cc? Therefore you can see this cc will be equal to complex conjugate of this much, and its complex conjugate you can see this is 1 over I h cross expectation value of px. Now let us substitute these two values here. Since there is here minus and minus, so that will be in fact plus, and so we can write this expression in this way. You can see this integral from minus infinity to plus infinity j of x dx, this will be what? This is h cross over 2im into 2 over minus I h cross expectation value of px. And so you can see this I times I will be I square, which is minus 1, and so that minus will cancel out, and h cross also cancels, and this 2 is also cancel out, and so our result is what? This is simply expectation value of px over m. So you can see the result which was to prove in this problem has been easily proved by using the expression for the probability current density, and in fact I have also utilized here an important technique so that the expression under the integral becomes the expectation value of momentum operator. So I hope now after these important illustrative examples, your concept regarding the probability current density has been very clear, and so you will follow the textbook and solve such problems for more